In this video, we'll introduce observational and experimental studies and highlight their key distinguishing features. We'll discuss one important concept in particular, the concept of random assignment or randomization. This is the element that allows us to infer causality in a study. There are two primary ways of collecting data for empirical research, by experiment or by observation. In an experiment, we manipulate a variable to study its effect. In an observational study, there's no manipulation, we just observe the natural variation in our population. Generally, the only true test of whether something is causally related to something else is an experiment where one group is exposed to that something and another group is not, and all other sources of variation between groups are controlled, such that the only difference between groups is exposure to the something of interest or the factor of interest. So say, for example, we're interested in whether caffeine causes an increase in output among academics. We might take a random sample from a target population of underperforming university academics. And remember, we take a random sample so that the results are generalizable to our target population. And then we might assign half of them to take a caffeine pill for 6 months and half to take a placebo or sham treatment for 6 months. And then following them up 6 months later, say, and measuring their output from baseline in some quantitative way. So this is an example of an experiment because we have manipulated the exposure of interest. In population sciences, we'd also call it an intervention study because we've intervened on our study sample. And as long as the experiment was conducted well, in the sense of controlling for all sources of variation or all sources of differences between the experimental groups, aside of course for the presence or absence of the intervention, then any differences between groups can be attributed to a causal effect of the intervention. In practice, to control for other sources of variation and ensure the groups are similar, individuals are randomly assigned to each treatment group. Such an experiment is then called a randomised experiment. And this would be our ideal type of study because it is the most valid way of attributing cause. However, in many areas, it's not practical and it's not ethical to conduct an experiment or to intervene on our sample. In such a situation, we rely on observational studies. So how might we look at the caffeine and academic performance question in an observational study? Well, two common designs are what's called a cohort study and a case control study. In a cohort study, we might take a random sample of new university lecturers, ascertain their caffeine consumption over a 6-month period, say, and then follow them up at their 12-month staff review. In a case control study, we could take a random sample of underperformers, i.e. the outcome, and a random sample of good performers extracted from the same population which generated the cases, and then look back in time and ask questions about their caffeine intake. The general feature of the case control design is that individuals are selected to participate on the basis of whether they have the outcome, and we then look back in time to measure the exposure. In the cohort study, we select people before they have the outcome of interest. So with this design, our target population was new lecturers because they'd not yet had time to underperform or to have the outcome yet. So following on from the video on sampling processes, there is a random element to how individuals are sampled from the population in both these observational studies. However, the missing feature that prevents causal inference in an observational study compared to a randomized experiment is that there is no random assignment of the exposure. And so we cannot exclude the possibility that any association found between our exposure and outcome isn't actually due to some other factor that differs between those exposed and those unexposed. So in our example here, we were interested in whether caffeine intake is causally linked to academic performance. However, there may be another factor that causes both better performance and a higher caffeine intake. For example, hours spent working. So perhaps it's getting up earlier and working longer that independently makes an academic drink more coffee and perform better, and hence generates a spurious correlation between caffeine intake and academic performance. If true, then giving caffeine pills to academics is not going to raise their performance because there is no causal link. It is confounded by the duration of working hours, and we call this variable a confounder. Confounding is the biggest issue that prevents the attribution of causality in an observational study. And you've probably heard of the phrase, correlation does not imply causation, which is a useful mantra to refer back to when interpreting results from observational studies. So just because we find an association, it does not mean that it is causal. There may be other factors that explain it. And there are all sorts of outlandish correlations that are clearly not causal. One of my favourites is per capita consumption of mozzarella cheese and the number of civil engineering doctorates awarded in the US. That has a correlation of 0.95. So just to connect and prime yourselves to future material, one way of controlling for a confounder, although it rarely entirely removes confounding like the gold standard of random assignment, is to stratify on the confounder. So what does that mean? So in our example, we would look at the association between caffeine intake and academic performance within groups of academics with a similar duration of working hours. For example, we may split the sample into those that work least, those that work normal hours, and those that work a lot, and then look at the relationship between caffeine and performance within each of these strata, as displayed here using contingency tables. So within each strata, there is no variation in the confounder, i.e. everyone has similar levels of working hours, or approximately similar levels of working hours. Hence, we are controlling for that confounder. The same sort of control can also be achieved by adjusting for a variable using a statistical model, such as a regression model. So just one last thing, we talked about the absence of random assignment of the exposure being the critical missing mechanism why we cannot attribute causality in an observational study. However, there is an exception. There's one special class of observational studies called natural experiments, where sometimes we may be able to make the assumption that the exposure has been randomly assigned due to some natural cause. And we'll discuss that more in the study design theme. So to finish, here's the new terms introduced.